If you've made it to this video on separation techniques, congratulations, you are almost done with Chapter 1 of AP Chemistry. That didn't hurt too bad, did it? Hopefully not. These separation techniques are things that we're going to use throughout the course, so I'm not real concerned about them at this point. But it's a good thing just to be familiar with the general setup and when I might use these different techniques. Distillation is a way of separating a mixture of liquids based on different boiling temperatures. So they have to have different boiling points, noticeably different boiling points. The setup looks pretty impressive, but it's actually a very simple procedure. All right, for example, my mixture of liquids will go in some kind of a flask. Let's say we've got, common distillation might be water and alcohol. Water has a boiling point of 100 degrees Celsius. There are different alcohols. Let's say we're using ethanol. Ethanol's boiling point is about 78 degrees Celsius. So they're noticeably different. That mixture goes into some kind of flask, and we'll start by gently heating the flask. As we do, we'll watch a thermometer. The first signs of vapors should be coming from the liquid with the lower boiling point. So as the temperature gets close to 78 degrees, I'm looking for alcohol vapors. Obviously, they're not going to look any different than water vapor, but based on their boiling point, that should be the alcohol. Those vapors then will run through a tube called a condenser. The condenser, they're kind of cool. Through the middle, it's hollow, but then around the outside, it fills with cold water. So there's a hose that'll connect to the faucet and will continuously run cold water through this tube. The second hose just goes down the drain. So the cool water from the sink will run through the condenser and then back down the drain. And we'll continuously run cool water so it doesn't warm. All we're doing in this condenser is just that. We're cooling the vapors to condense them back down to the liquid phase. So that in this final receiving flask, I have what's called the distillate. It's the first liquid that comes off the distillation. In this case, it should be the alcohol. And I could test that by taking a small sample and lighting it on fire. The alcohol should burn. If it doesn't burn, I may have some water in there. So maybe I wasn't watching my thermometer closely. If that temperature starts getting close to 100 degrees, I could be boiling the entire mixture. And then I really do have a mixture of liquid, water, and alcohol in my final product, which I would not want. And so that might be kind of an error with this distillation apparatus. You do have to monitor the temperature so that you only keep it at the boiling point of your first liquid. So that's kind of a common technique for separating liquids, especially based on boiling points. It's kind of fun. Pretty harmless once you have it set up. I'm hoping that in first year chem, you all became masters of filtration. Filtering is a way of separating a mixture of a liquid and a solid. So most of the time you did this with a precipitate. Maybe you formed some kind of a precipitate, or maybe you formed like copper metal or something like that. And then your other product was a solution, so kind of a liquid solution. So we've got a folded piece of filter paper that goes into a plastic funnel. I usually put the funnel on top of a Erlenmeyer flask. Here they've kind of got it clamped to a ring stand. That's fine too. They've got their mixture kind of flowing down a stirring rod or something like that. We usually just say you kind of want to swirl up that mixture of solid and liquid and gradually send it through the filter paper. We don't want to get too excited and overflow the funnel or anything like that. We don't want the mixture to get kind of trapped behind the filter paper. That's a common error when people get a little too antsy with their filtering. But eventually then the solid should collect on the filter paper. The filtrate is that final, it's usually a solution. We'll put that down. That drips through the filter paper. At the end of a filtration, it's always good practice to run a little extra distilled water through. Let's say, for example, my filtrate solution was like sodium chloride. Well, that sodium chloride solution, if I let that dry on the filter paper, it's going to add mass. The water will evaporate overnight, but the sodium chloride will stay on the filter paper as a solid, and that would add mass. So it's always a good idea, if you have time, to rinse your final precipitate or solid, whatever it might be, with extra distilled water. That filtrate solution, sometimes we don't need it. We can dump it down the drain. Maybe we only want the mass of the final copper solid or whatever it might be. If we want the mass of the final filtrate solution, we often need to boil that. We'll put it on a hot plate, evaporate the water, and then we'll take the mass of the remaining solid from the solution. So that should be a technique that you've done in the past. Filtering is very simple. It just requires a little patience. The final separation technique that they've got listed here is chromatography. We'll do a little chromatography second semester. It's another way of separating solutions, this time based on an affinity or attraction to a particular solvent. So you may remember from first year Chem 2 that when you look at atomic structure, and sometimes you can kind of predict that certain particles may have an attraction or an affinity to each other. Maybe they're both polar molecules and they have a partial positive and a partial negative end to them. And we would say those particles then have an affinity toward each other or an attraction toward each other. That's kind of what we're looking at with chromatography. It's usually done with some kind of paper. In the lab, we can even just use filter paper. We'll put a drop of our mixture, usually down toward the bottom of the filter paper, and we'll kind of let that dry. And sometimes we'll kind of dot it a few times. We'll let it dry. So we'll have a nice little sample of our test mixture, our mixture solution, down at the bottom. Then we're going to let that piece of filter paper sit in some kind of a solvent. So here they've got kind of a picture. This would be down in the bottom of this dish, some kind of a solvent. And often we'll take our little mixture and, maybe we'll put like a drop of it. And we'll kind of let that dry and let that drop concentrate. We'll put that down toward the bottom of the filter paper. Then we'll just gently let the filter paper sit in the solvent. That solvent gets absorbed by the paper, and eventually it hits my mixture. Now, depending on the affinity of the solvent to the particles in the solution, we'll see those different liquids travel up the paper to different points. This one here, I think, is actually, this picture is black ink. Black ink is a combination of all kinds of different colors. So as you see the solvent get absorbed by the paper, all those different components of the black ink move up the paper and get deposited at different points. So I can kind of tell here that whatever particles travel the farthest, these particles had the greatest attraction to the solvent. So it could be like a mixture of dyes, and I can see that, well, the yellow dye is deposited right away, and then came like the red dyes. But the darker colors, maybe the blues or purples, those dyes, the greatest, there we go, attraction to the solvent, those will be deposited toward the top of the sheet. This works really well with the pigments in, I'll say like a leaf, a fall leaf that's starting to turn colors, has different pigments in it that are different colors. You could take a sample of those pigments, the mixture, and let it run up a chromatography sheet like this, and you'll see that, there's all kinds of different components in that leaf then. There's yellow dyes, and pigments. There's orange pigments, and there's green pigments, and they'll travel at different points up this chromatography paper. We'll use this to separate components of a grape juice mixture. There are different components that add color, that add flavor, that add odor, and they have a different attraction to the solvent. So whatever is deposited first must be the least attracted to the solvent, and then whatever is deposited at the end has the greatest attraction to the solvent. So it's another way of separating a mixture of solutions, but instead of it being based on like a boiling point, it's kind of based on intermolecular attractions. And then we can look at the structure of the particles and we can predict, well, based on the structure of the solvent, whether it's polar or nonpolar, we would predict this particle to have the greatest attraction, and this should be deposited first, or this should be deposited last. So it's definitely something that we're going to look at after we get into bonding and atomic structure and intermolecular forces. We'll run a chromatography that'll be kind of similar to this one.